Okay, so welcome. So we are discussing this afternoon the creation of active devices, and as we saw in the last lecture, there's a significant amount of area being processed in terms of semiconductors. So when you look at the amount of areas that we are now covering, this is just for electronics. This is an outrageous amount of consumption, and it's still growing. So at the moment, we cannot make as many semiconductors as we would like to. This is mainly due to the fact that simply the capacities are not there, and there's a tremendous amount of not only of this, but at the moment, especially the amount of, because of the powertrain or the e-mobility, the amount of semiconductors which are needed is higher than what people can produce at this point. So both in Europe, in China, and in the US, people are trying to get the capacity. So what we learned last time was that this is done contrary to what is predicted here. So there's the increase of the size of the wafers, and there was this parallel idea. We make a wafer, and you just saw how this is done. It's a highly automated process, and there was one idea which first of all, we had to make the wafer, which in itself is a big story, because you should have this idea. There's a pizza, but on the z-axis, this is an atomically clean surface. Yeah, so there's a surface which on the z direction is atomically clean, so just very flat. And this making of a wafer sounds a bit ridiculous, but it has to be relatively cheap. And because we think per process step, so a process steps cost a certain amount of money. And because if we can make more devices with a high yield on a bigger wafer, we win. And that's the idea. So you try to make these rods as large as possible and also as clean as possible. This is the idea. Yeah. So this rigid which you can get there is actually they're starting to weigh several hundred kilograms. So this is really an issue. And then you create them, and then you have to polish them mechanically and later chemically to make an atomically smooth surface. Yeah. Why does it have to be atomically smooth? Because we typically after that incorporate, and that's what you saw with the video. You put here, we are now on it's a gas wafer, but it's the same idea. You're going to a process where you add atomically individual atoms. Yeah. And you saw with this video, which I like very much, I don't want to repeat it, but it's a very nice idea here. So just to tell you what you see there, I don't want this video. Let's just forget about the stupid commercial, but it's what you see is to create something which has a very high value in the uniformity, but at the same time addressing relatively big wafers. Yeah. So the trick is, how do you get an atomic surface on something which is of course flat? These are not, in this case, these are not silicon wafers. These are silicon carbide wafers. They're in 6-inch. Yeah. But you see, the idea is you want to have as big as a wafer. You want to put something on top, and you want to grow homogeneously atom by atom, which is quite strange. So on this, you have 300 millimeters, and on the other dimension, you have essentially 10 to the minus 10 meters. And so it's comparing 0.3 meters to 10 to the minus 10 meters on this axis. And you saw how this is done in this machine. The trick is, it's put there, and you saw this as much as I want to show. You see the thing, it's put in, and then it's turning. Yeah? So this is the idea. So this is getting the free wafers, getting them back. You get a new one. And the trick is then the whole wafer starts spinning. Yeah. And why do they spin? What would you guess? Why do you start the spinning process? Yeah, so it's very clear. So it's always, if you want on a surface, if you want to have as little as possible dependence on the position, you spin so that the coating which is done is very homogeneous. Yeah, and this is so in this direction now it's turning. Yeah, this is what we just saw. And there's a couple of requirements which you have to do. So what you these precursors are inserted in a laminar flow, and this is what you saw in the earlier video, that you saw the creation of a gas flow which is totally laminar. Yeah? So there's no disturbance whatsoever on the top of the smooth surface. And this is the big secret. How do you insert something that there's no it's a fast flow, but you have to create a condition that there's no turbulences in the gas itself. Yeah, so this is very important. So it's a perfectly laminar flow, like on the surface of a wing of an airplane, so perfectly linear, without turbulences. And then you create, especially by heating, you allow first of all movement once the atoms are put to the surface so that they can align. This you do by the right temperature. And the second idea is that you put these very unstable gases in the right content. So there's partial pressures which are just in the sense, because the partial pressure for one material is not typically the same one for example, for gallium and aluminum. They're different. So you put them in the right pressures that you get a one-to-one combination of the atoms deposited. Yeah, in combination with the temperature, and also the total pressure of the other gases in there. For example, hydrogen, which are and nitrogen, which are also in there. You get a mixture, and the target is that these polymers, which are essentially they're decomposing, and that the organic part goes off, and they drop the metals, and there's also the arsenic in this case, or some other group 5 material, and there could be nitrides, and then one-to-one you get a composition of this material. So for example, this is now given for gallium arsenide, or could also be gallium nitride. The same happens for silicon germanium. Yeah, so silicon and germanium are the two atoms which form, and then you get more or less perfect surface for this. It's crystalline, and it needs a growth rate. So the advantage is that you saw that it's a macroscopic process. It didn't require vacuum, because when you remember this video, there's no special requirement needed for the evacuation or something around the wafer. It's a lower pressure than what we have in this room. There's also a protecting atmosphere on top. So there's, as I said, nitrogen and hydrogen around, and then, or ammonia, and then so there's no oxidation or something, but the overall conditions are reasonable, so that you can easily get them. So you put in a wafer, as we just did, and within seconds you can actually start growing, which is not, for other things, is not so easy to do. And the trick is then, why is this procedure so nice? Because you can also grow at a substantial growth rate, because you make an atomic growth, but you also want to create a significant layer of this, because if you're thinking you're depositing an atom by atom, you're turning crazy. Yeah, because it just, and for example, one application where we need this, for example, all the white LEDs are produced in this way. So all the lights we have on this planet, they are grown in this fashion. So you need a certain growth rate just to make it happen, because if it takes days, then it wouldn't be a good technique. And this MOCVD here, this chemical vapor deposition, has a growth rate in the range of 1 micrometer per hour, which is already good. And for LEDs, for example, you need a couple of microns to do something useful. Same for electronics. So within reasonable time, you can produce good surfaces. You can produce a growth rate, which gives you a device. And through this very nice design of the reactors, you can actually get a decent homogeneity. And you saw the wafer spinning, and the spin actually there's still some dependence of the over the wafer, of the thicknesses and also the dopings, but it's reasonable. So it's predictable and useful. Yeah, so these are the criteria which we are after when we grow materials. Yeah? And it's a big gas story because you have to, these things are big gas cabinets essentially. So it's always the reactor, but you saw the machines are relatively big. And what sounds so simple, yeah, is the creation of the right gas stream, because you're dealing with these precursors which have the metals in there. They're extremely unstable. Yeah, so they're decomposing if you don't treat them well. So the whole story is getting a gas cabinet, and that's what you saw with the reactor. It's essentially a big gas cabinet which supplies all these gases in the right partial pressures, in the right temperatures, and in the right concentrations, and cleanliness, of course, because anything, that's something you can easily imagine. If there's any other material around, especially in the precursors, they will also be incorporated. And as you know, anything which is not the substrate material will form some kind of doping, which is typically not desired. And so that's something which you, but the cleanliness is reasonable in the sense that once you put the gas on top and the stuff which you insert is clean. So clean means six nines after the comma, so 99.999999. This is the concentration which you have in the gases which we insert. So that makes it also expensive a bit. So that is then, so just to, it sounds like a good method. It is one, but there's still these requirements because it has to be crystalline and it has to be extremely clean to make happen what we wanted to do. Just to contrast a bit what you, so here you see such a reactor when it's open, and you see here that there's nothing in the middle, and this is in this case the stream is starting from here, so it's this is where the gas inlets are, and they're floating here, and then there's the gas. So this stuff is turning, and then here the gases are taken out again because you're putting very high numbers of volumes of gases under these conditions in there. So we come to EAF, you will see there's silos of real, where we make that, there's silos of these extremely pure gases, and it's especially also hydrogen. This is really a large amount, so you have a high throughput to make that happen because you're just depositing the metal, but the rest has to be also inserted and then also discarded. So that's the challenge. There's another method which we also, especially where we work, are using. This is MBE, molecular beam epitaxy, is completely different because it's done in vacuum. So in this case, you take a machine and you first of all install a vacuum. And vacuum in this case means pressures of 10 to the minus 9. So 9 orders of magnitude where we are here when speaking. So essentially you have a piece of space in the clean room. Yeah, so you essentially, there's nothing. Yeah, so there's nothing in there. And the idea is the following, that you have a wafer and you again want this atomic deposition. Yeah, so you want to the atoms should go straight on the wafer in the right composition. And because, and this will be something like a meter. So you need an atom in an atmosphere which is clean, that there's no encountering of other atoms for about a meter. So the free wavelengths, so the free non-collision wavelengths, as we say, should be a meter, which is not, of course, if there's any gas around, there will be collisions immediately. But in this, it's so evacuated that there's no encountering from the sources here. These are guns, as we say, so they're just evaporating a metal or some other sources. And then the sources target to the wafer, and they are dropping, so to say, without any collision. They're arriving at the space of on the wafer. It's again heated, yeah, and then you get this type of behavior again. So you have a substrate. So this, in this case, would be the underlying material, and every new layer is put on top. Yeah, so there's the beams of the gallium. You need to heat, because once they arrive, then these balls have to arrange themselves that they are sufficiently mobile once on the surface, but it's a overall it is a growth which is atom-wise again. And in this case, the growth rate is much lower, but it's much more precise because you really deposit the atoms individually. Yeah? And why is this important? Because for electronics, we are getting to these points that the channels are getting so small. As you know, in CMOS, you can understand that nicely when you have a MOSFET. And the MOS is only 2 atoms thick. So, and the same is true for the devices we make. So there's the barriers and the thick layers are just a couple of atoms, because to get the speed, so that then you are depositing changing materials with 3 atoms and another 3 atoms, and this you can then do nicely. Yeah? The trouble is with this procedure is to get the machine into this state, you need about 8 weeks. Yeah, so you have to get this evacuation, you start pumping, and then you start heating the whole chamber here, yeah, just to get everything out which is not belonging there. So it's an extremely clean process, and then this is nice once it's working. But if there's any problem, and you have to repair and then exchange something, then you are a bit stuck, because then you have to open it and you have to repeat the procedure. So these things are constantly working until the sources are empty, so to say. So you try to never have to open them. The wafers are transported by a lock system, so they are put in here and removed. So there's a locking system so you don't break the vacuum. That's the idea. Yeah? So you just have a vacuum which is constantly maintained, and by a smart system of locks, you have finally put the wafers in here, so that you can once one wafer is grown, you can remove it and put another one without breaking the vacuum. Yeah? One thing of this plot is wrong. Normally the sources are on the bottom, because you put the wafer on the wrong side, because what you want is, if there's any dirt still remaining, that it will drop gravitationally back. So you shoot with the gun from the bottom, because any dirt which might there should not stay on the wafer. If there's anything still in there, you always want to, there might be some particles or whatever, that just make sure that they're not in there. So that's always a risk. And you can actually see this. This is the monitoring of this, because there's a read system. This is an idea that you diffract electrons on the surface, and when you have this growth of the MBE, you changing constantly the surface, so you will all the time, when there's a step of such a new layer formed, the diffraction of the electrons, because the electrons can also travel freely, and you get an image, so you can actually observe the growth of atom by atom on a pattern of diffracted electrons. So this is a very nice control of the system. Yeah, that you so you put electrons on here. This is the gun, and you look at them here. So there's a pattern forming, and for each step, over time, you get really an observation how these layers are evolving. Yeah? So that's maybe electron diffraction, which helps you to do that. Yeah? So this is very nice, but the growth rate is typically not an order of magnitude lower, but factor of couple of 5 or so for the same material. So this is how we want to do it, and most of the stuff you have in your cell phone is done in this way. So for example, the HBTs which you use are grown by MOCVD. Second material, you can also grow them by MBE. Then the layers are nicer, but they're more costly, because you saw that for the MOCVD, you can put in this case it's 11 wafers, I think, which you get per batch. Yeah? For MBE, it's typically can also be multi-wafer, as we say. So there's not just one wafer in the chamber, but several. But it's not so easy to put 11. And so it's always the differentiation is always the area you can use to make it cheap, to make it homogeneous with the same process, and just expand on it. Yeah. So that's, and what is quite tricky is this ultra high vacuum, because this is something you don't want to break. That's molecular beam epitaxy. You shoot single atoms on a surface. This is good. So, and then we are going to a processing clean room. So the MBE systems needed clean. The MOCVDs you could still do in a gray room, so you wouldn't necessarily have to put them in a clean room. But when you are going to the ultra precision, which we need then for the processing, you have to change to a clean room. Yeah, so, and clean in this case means there are various classes, and especially for those big pizza wafers, you need an ultra clean environment. And just to what does it mean? There's the definition. There's several classes of clean rooms, but just to give you one system is quite nice. A class 1 clean room means you have one particle of a certain size within a cubic foot. So volume like that, and you have one particle in it. So it's extremely clean. And this you need because any particle which falls on the wafer would kill any device which you would produce. So this is the ultra clean room. And then we have a class 10 clean room here in Freiburg at the EF. It's a bit, so it has 10 particles of this type because we are not so much yield limited. And of course, with every particle you have to remove, the energy cost and the cleaning of the procedure is needed. And there's always this very strange light. Does somebody know why there's yellow light always in clean room? I think you have seen it. It's always when you see these people, you see people, if there are people in there, they're very covered with everything, and the light is always yellow. Why is that? When the light is yellow, what is not in there? So white light is all the colors, but if you have yellow light, what is then not included? It's the blue. The blue is in this case is not so nice, because with the blue light we are developing certain how do you say, luck. It will be on. Pardon? Photo lac. What's the English word? It's photo resist. Sorry, the resists. Thank you. It's the resists which are exposed to UV light, and then they change, and I'll explain that in a minute. So the resists are sensitive to blue light, and so we put them in yellow. We couldn't go just red, because then you wouldn't see anything. You need certain distinction also to see things, so that's why it has to be a mix of colors. But you're discarding anything which has the blue light for the resist development. There's a second idea which is related to fab, is that I promised you multiple chips, and here you see them. So each of these reticles, so each square is the same mask. Yeah, so the devices are not taken just as one because they are small. Yeah, so that's typically the reticle has the size of something like 20 by 20 millimeters. So the maximum chip size you could think of is typically, for RF at least, is in the range of millimeters. And for the microprocessors, you know, these chiplets which you have for the size, if you put 4, you typically you have this knowledge of how a processor looks like. You typically have multiples in them. And each of these chiplets is just the size of this, and then you put repeat, so to say, the same structure on the wafer. The repetition is to make the thing cost efficient, yeah, because you repeat with the same step. So the wafer is exposed one step, and then you get so and so many chips per step. Yeah, so you repeat the processes, of course. It's not just one step, it's multiple chips. But for the sequence of steps, you get multiple devices. Yeah, so that's what you see here. And now the trick is, how does this work? How is this made, and what do you need for that? So we're starting with such a wafer, which is then, and what steps do you need? And there's a couple of typical processes which we need. Sometimes they're really underestimated in their complexity, but some are very obviously critical. For example, lithography is the defining element, but there are also some relatively easy things like etching and deposition, which are also very, very important for this. Yeah? the first thing is what is processing in relation to epitaxial growth. So epitaxial growth is still fully 2D normally. So you have first of all this wafer, which has just the surface, and then you put 2D, you put something on top. That's normally relatively planar. You can also do a selective epitaxy, that's also done. But typically you have this idea, you have a wafer of one material, and then you add additional layers which form the active stuff, which is 2D, and then you go into processing on top. Yeah, so this is already processed. You see there's something structured seen from the top. And what are the things you need to do? The first thing is when we are defining devices, you can dope the material, the semiconductor, in various ways. We talked about this already a little bit, and there's now multiple methods of doping. If you do epitaxy, how do you dope them? So what is one way of doping something? So you have layers. How can you dope easily? So when we go back to this here, how could you dope this? Yeah, and the idea is you, for example, in the MBE, you just have also some source of silicon. Yeah, and I said normally you are actually, if you're not careful, you are doping already with the impurities. So anything which is in there which doesn't belong is already doping. Yeah, so it's very tricky not to dope, but once you do that, you just add, but then it will be just 2D. Yes, you have it everywhere. Yeah? So this is one easy way of achieving some doping. Yeah? With the implantation, you just have another method which is area selective. Yeah? And this is indicated here. So, for example, how do you make a simple PN diode? So PN means one which has an electron doping and the other one which has a hole doping. Yeah? And it's just like, you see that there, this is how they made the first devices. You just, on this wafer, you shoot for certain areas, you shoot the atoms in there. So you take a gun and you just, it's like hammering them in. So it's a relatively rough process. So from the top, you take a source of atoms, accelerate them, and by a certain energy. So here in this range, about 25 kilo electron volts, so relatively strong with the doses per area, and you shoot them in. You kill the crystal by that. So you need to, afterwards, you need to cure the crystal, because similar to what we have been doing here, it's this like a ball game. So you have the balls, the atoms, which is not wrong to say in this case, and then you shoot additional in, but the structure will be in some kinds of killed. But you use the same method which we use also here to make the crystal nice again, which is warming it up. So you warm it up, so there will be some crystal arrangement. So the crystal is cured, and then if it's implanted, some of these electrons will be replaced. So some of these atoms will be replaced, for example, in n-doping by silicon in this case. Yeah, so you will just replace them, and then you get some kind of doping. Yeah. The surprising thing about this implantation is that it's a distributed process. So you really shoot them in, and you see there's some profiles formed. Yeah, it's like, so if you're hammering the atoms in there, you say this is a root process, and it is very root. The surprising thing is how good by now you can make that in its depth also. So it's because the devices we have these days, they are only in the depth, they are only a couple of atoms deep, and you need to stop somewhere, and you see you get some kind of profiles. Yeah. So this is a statistical process, and especially when you shoot things into a crystal, you have to stop somewhere. Yeah? For some dopings, we need to be very precise. For others, we don't mind. For example, one process which is very root is the isolation process. This is a very simple one, because when we do an isolation implantation, why do we do this? Because if you are on the wafer, here it's depicted on the right, between the individual chips, you want to kill them, kill everything, because there you want the chip really to stop. Yeah? So you make an implantation process which really kills the crystal there. This is also the area here, these frames where you're going to dice. So to cut the chips out of the wafer. Yeah? So there a mechanical or whatever procedure will cut to make chips individual afterwards. Yeah? And this area is formed by isolation implantation. So you put something in which makes the crystal simply dead. Yeah, this is important. Yeah? While other implants, this is the doping ones, they will be electrically active and they activate both in N and P. Yeah? And there the trick is also, because if you remember what we looked at last time, the definition of the fat we looked at here. So for example, the stopping process. So just remember what the size is. The thickness of this oxide is only a few atoms. Yeah? And you see the definition of the implant profile. So this is only a couple of nanometers or so. And the trick is to hammer something in, but then to stop. Yeah, because you want the channel to be doped maybe, but then also to stop, because you want no electrons to flow in this range here. So this has to be very defined, and this is a high art, something which is a relatively rude process, but learning about the definitions to make it so nice. Yeah? So because if you have a contact which also connects here, for example, then you have leakage currents, which you are trying to avoid. Yeah? So this is not something you want. So, and so even such a normal process can be relatively tricky. Yeah. The next thing is then, this is the high art, is the lithography, because this is really the changing element between things that we have, and the very difference here between this generation of iPhone and the next one is the lithography of the process used. Yeah. And why is it so difficult? Maybe so. Why is it difficult to make structures which are only a few nanometers long, so to say? Just what is the first idea? Why is it critical? What do we need to make something like that? What would you say?
The problem could be of the precision that we want. Suppose we are throwing atoms at a specific place.
Yeah.
And you said that it takes a statistical form. So
Yeah, but the idea is, first of all, what is defining the structure? Maybe you start like that. How do you structure something? What methods do you have? And the easiest way is, of course, and that's still done in some things, is just to set a contact. So you imprint. You can really define a structure by printing. Yeah, so you take a resist and then you mechanically imprint something. So you form structures by real mechanical imprint. This is still done and works to a couple of, let's say, a couple of 100 nanometers, micron range. This is something you can still print. Yeah? But below that, which methods do we have, and especially what is important in these methods? So when you just try to structure something, what is the guiding principle? Maybe go back here. The trick is that you have essentially a planar thing, and then how do you structure this? For example, if you say you want such a pattern that is indicated with the red light here, how can you do that? And the trick is, you need a mask, something which says where is something or where is something to be removed. Yeah? Both is possible. And then what do you put from the top? Which options do you have to define that?
light, wavelength.
Yeah, there's light, and why is the wavelength of the light important?
Because the smaller the wavelength is, we have a higher resolution in the mask.
Yeah. That's the principle of the microscope. So the first idea is when you have a microscope, you can only see. So why can't we see atoms? Because their size is much smaller than the wavelengths, which, for example, is emitted by these lamps. Yeah? So just to give you a size, what is the range of the light we use in this room when we just look? So the optical light, what is the wavelength? Roughly. Optical waves.
400 to 800 nanometers.
Yeah, so let's go 4 to 7, 800 nanometers, 400 to 800. 800 will already be infrared, 700 is the red we see, 400 is the blue we see. Yeah? And what is now very fundamental is that most of the structures we use in electronics, from their size, they are smaller than the optical light. Yeah, so you suddenly need something to expose, and first of all, how to explain lithography. First of all, how does it work in principle? So the first idea is how would you do it if you were baking bread or making pizza? You would imprint, but imprint mechanically is limited to precision in the micron range. That is where mechanical things are starting to be critical. And that's why you do it differently. You just put a layer of something which is sensitive to something, maybe electrons or light. Yeah, and then you have both a negative or a positive process. You can either, in this case, you can expose it. Yeah, and the trick is, by exposing it to light, you change the properties of the resist. So if the resist is not treated by light, it will still be resilient towards certain chemistries. Yeah, and if it's exposed, if you treat it with a certain chemistry, then in these spots the stuff will be removed. Yeah, and then you will you just put something planar on top, and if you do it right, some metal will go in and some metal will stay on top. That's not easy, so it's PowerPoint engineering. You have to be careful. So we spend quite some time to make effectively that happen. But then the idea is at least that you then remove the resist by just other chemicals. So you need two chemicals, one which can deal the exposed stuff, and the other one which removes the non-exposed stuff. Yeah, and then you kill this stuff, remove it chemically, then also this metal will go off. And what will happen is that these structures remain. Yeah? So that is a positive process, because in some ranges where you expose, you put something. Yeah? You can also turn it around and expose these and have something standing, which was, so for example, you could have a material, not a resist material, but something else, and then you remove the other stuff, and then it's still something is still standing. This is also work in this other way. Yeah? And as you said correctly, what do we have as option for the exposure? It's these resists are sensitive to light. Yeah? And what happened now is that in the time we are living in, that the normal, mechanical stuff is limited, and then the wavelength is defining what we can use as structures. Yeah? And maybe just to explain what is the idea, is that there's two quantities which we have to observe. The first thing is the lateral resolution, which is essentially saying how small can I make a structure which I'm defining. Yeah? And there's only the principal thing which influences that is the wavelength. Yeah? So we can typically see structures which are in the range of the wavelength. Yeah? Say that again. We can only see structures which are in the range of the wavelength, or where the light has a smaller wavelength than the structure. So it's limited to go low. Yeah? You have then two technical parameters which are in there. So the first thing is the numerical aperture. Yeah? So this is what is defined by the microscope. So you just open, because you look at this with a lens, and this forms an aperture, and this is a certain value which is in the range of, as you see here, in the range hopefully of 1 or below. That's already a very highly qualitative optical aperture. So that if you take that, and then there is also some tricking factor which has a lot of ingredients. So sometimes you can even go, you see that here, the wavelengths in the top case of the 284 nanometer. So the minimum feature size, which you then can define by tweaking these more technical parameters, you might be able to go maybe to 165 nanometers. Yeah. And why would we want to do that with pure optical light? And we are still using these steppers a lot. This is because it's a parallel process. Yeah. So the idea is that you expose the wafer in parallel. So all the reticles, as we say, all these chips which you see there, are exposed with one shot. Yeah. So you put them underneath and you shoot by a lamp. Yeah. And you get parallel exposure of all these devices. Yeah? And that is fantastic because it's cheap. Yeah? So sometimes the step, it's called an optical stepper because it's not fully exposing a full wafer. It will still go a little bit in the reticle, so you will still not expose the full wafer. So you will have shots for each reticle or for a number of reticles, but you will get still, when you think that such a processor can contain 10 billion transistors, with one shot in such a reticle, you can expose 10 billion transistors. Yeah, so there's a lot of parallel devices which you can process. Yeah? So that's the stepper. The trouble was, at some point, people decided, that happened around the turn of the century, that the optical light was not sufficient to fulfill this process. Yeah? So there was a limit in the resolution. So by the way, why is it not easy to make light below a certain wavelength? What are the typical limits which you might know about already? So why don't we just take UV light and continue? What is the trick or the problem? Remember what you need for a microscope. So what is a microscope made of? It's very simple. So what do you grab when you have a microscope? Or what do you have there? The aperture. And what does the aperture consist of? Lenses, yeah. And there's a simple thing that for a certain wavelength below visible, there's simply no lenses. So quartz and all the things we make lenses of starts absorbing heavily below a certain wavelength. Yeah? So this idea that you can focus and stuff like that, that only works with the materials we have to a certain point, and then it stops. Yeah? So with the, and I didn't say that, no, sorry. There's also I missed to say that, there's also why we need to focus, because we also need a depth resolution. So it's not just enough to have, here you see that, it's not enough just to have the resolution, you also need to focus in a certain depth, and the focus depth you have is a very similar formula to to what you have with the resolution on the surface. So there's the same idea, but you need to be able to focus there, and at the same time also to resolve. So these are similar equations. One goes with the linearly with the numerical aperture, and one goes with the square, and then there's a lot of tuning then based on the quality of the optics. But these factors are typically in the range of 1 and lower. Yeah? So in both directions we are essentially limited. Yeah? And then people still wanted this parallel exposure. Yeah? So what options do you have now to go down to the nodes? So for example, just to give you a feeling, so the RF nodes we are in, they're presently 40 nanometers or 22. But if you had a memory, if you think in memory, what is 40 nanometers in memory, or maybe in iPhones or Samsungs? When was that? 40 nanometers of memory technology. Is this still state of the art? No, it's iPhone 2 or so, or Samsung, whatever. So it's nearly not 10 years, but several years back. So what I'm trying to say is the lithography methods which we have optically available are outdated. Question is now, what can you do now to, but obviously we have iPhones and we have memories which have feature sizes of 2 or 5 nanometers. How do we make them? What is the trick? What are used if we don't have optical sources and if we don't have lenses? What can they use? What is a strong source for very deep UV light? How can you create deep UV light if it's not done by a typical light source? Which, pardon? Yeah, electron beams is correct, but this is another story. It will come a little bit later. But how could I make how can I make something which emits at, let's say, at 10 nanometers or 13, as we have here, 13? What are you doing then in order to make that type of light? It's a plasma. Plasma you can heat. So if you heat electrons and you just beyond the gas, you just put a gas which still has atoms, you heat it in a way and excite it in a way that everything, that you have electrons and ions flying around freely, which is the fourth state of matter. So it's solid, liquid, gas, and plasma. And that was the solution for the sources. We still don't have the lenses. Yeah? And what can you replace a lens with if you want to go optical? Any idea? Mirror, yeah, and that's good because you can still make mirrors at this wavelength. Yeah, I mean, it doesn't sound like much, but when you, so here's the trick. So how you do it? So this is an optical stepper. Yeah, the thing to observe first of all is that you have a mask and you put a pattern, which then is some kind of camera effect. So you say exposed and non-exposed. You want that intensity distribution. This is what you really get. And then what you have to optimize, of course, is that you then etch and then you see the rose line is then the actual response of the resist, which looks more or less like a square. So that's already quite good, yeah. And here, this is still the optical stepper. So here you have this reticle. This is a big mask. First of all, you are focusing because you're starting with the structure. The mask layers are macroscopic. So you put the chip as a relatively big structure in exposed and non-exposed. Yeah. So and then it's reduced in size to the actual size of the wavelengths, to the chip size that is actually positively defined on the wafer. Yeah. So that's what you see here on the right. And that's why you need these lenses. And the trick is now, this is where Europe also is very good. So this still looks like a camera. So the size of of a stepper, as we say, this is a reasonable equipment. So a stepper today looks like, for example, for 248, which is a normal eyeline or UV stepper, that is it's not even a room. So it's something like size of this door in 3D. So this is around what you need then. Yeah? When you then go to the extreme stepper, and Europe ASML is still the company which does that for the whole planet. This is more like 3 garages next to each other. Yeah? So this is a huge thing. Maybe we can isolate something which has a reasonable size. So I think this is about a meter or so. Yeah. that you get a feeling. So it's more like 3 rooms adjacent. Yeah? And what is the problem? It's still the same principle. So you have a camera, but the light source are droplets of a certain liquid which you excite by a laser, which creates a defined plasma. And they're producing about 2 watts of plasma power in this thing. The power consumption is about a megawatt. So it's pretty crazy. Yeah? So it's a real high. So the efficiency is 0. It's just to get 2 watts of power from essentially a megawatt of electrical power. So that's the problem. Just to prepare these metals, which are then made to plasma. And then you have a very stabilized, crazy mirror system. You see the flow there, there's the gun. And then you, by making several of these optical imaging things, you just finally arrive at the wafer, which is then exposed. Yeah, you need about 15 people to operate the system. 15, 1-5, just to run the stepper. So that is. So we always say it's easy to do this Moore's law, but it comes at a price, because the problem is especially the stabilization of this, because you need to run it in a repeatable manner. Because remember what you want to do. You want to do structures in a defined way, and you want to do them in billions. Yeah? So you have to make sure that the conditions which you maintain, which is mostly temperature and also the reproduction of the light, to keep that very constant. Yeah, that's the whole story. And that's why we get iPhones, yeah, or memories, yeah, because we can do those lithography steps. But in all over Europe, I think there's 1 or 2 of them. Most of the production is done in Taiwan these days, where they have also some of the US fabs have such a stepper, like Intel. Intel by now is a bit behind, so they're doing 5 to 7 nanometers. TSMC, Taiwan Semiconductor Manufacturing, they are doing the latest ones, which give us the memories, the flash, and especially also the SRAM coming from Samsung in Korea, South Korea. So this is how this happens at the moment. Cost is, what is the cost of such a thing? 3 digits in millions. So really crazy. I think 150 million euros. Quite a challenge. Somebody said correctly, what is the alternative? We can use light, which or it's not light. We can use something which has a much smaller wavelength. Yeah? So we can do the exposure not by light, but by particles. Yeah? And as you know, matter is light. So an electron has a wavelength. Yeah? So and then we call that an electron beam. Yeah? So you can isolate beams, you can shoot electrons on a surface, very defined way. So it's very simple actually, because you have a charged particles which you put into a deflection chamber. So by electrical and magnetic fields you can actually focus them. And the nice thing about an electron beam is that the wavelength of an electron beam is about 10 nanometers. Yeah, so, and there you really use the idea of light, but it's a matter which has a wavelength. Yeah, so there you learned in physics that matter is a wave, and here you can really see that it happens because a particle has a wavelength. And this wavelength is now defining my gate, yeah, because what you do is you put again a resist. So this is the resist, and then the red bar is where you shoot the electrons to the surface. So this is the width of the electrons, which you focus on the surface, because you can do this essentially by electric fields. And then they scatter, and the scattering is defining the exposed region, because when you shoot them on the surface, there will be some kind of reflection also. And the yellow bars are just what you really expose them. So the E-beam is smaller than what you finally expose, but you get still a very small number. Yeah? So, for example, what I'm doing every day, with the people with whom I'm cooperating, they are making regularly 20 nanometer gates with this process. Yeah, so then you take the 10 nanometers of the electron beams, and you reduce these scattering regions to 5 nanometers on each side, and then you get an exposure. This is nice and easily done. By the way, where this is also used, something we tend to forget, there has to be a mask also for the optical. So here in the optical stuff, somebody has to create a mask set. Yeah, so that means that there's also something which already is useful for making an optical mask, and this is also written by these e-beams. Yeah, so you can you write these structures which you use then for exposure by an e-beam also. So that's also where it's used. But here this is how it looks like. So then this is the deflection. So you generate electrons in a vacuum by field emission, and then you just accelerate them to a relatively high energy that they are a beam. Yeah? And then you take capacitors and some deflector units just to move them around. So you can scribe them. Yeah? So you can move this beam. The problem is, and I think somebody mentioned it already, I also have it on the foil, this is a linear methodology. Yeah? Because in a camera, you just expose 10 billion transistors with one shot. In this case, you write every transistors each. And you can easily understand that doing that deflection 10 billion times, it will take quite a while. So this procedure today is not really feasible to write very fast and many transistors for CMOS, because especially for memory. We can use that if we are in the RF, if we have to do, let's say, 40 gates per chip, that will work. Yeah? But if you have to do 10 billion transistors per chip, then this method will not be good. Yeah? So it still has a very high precision. So that's the nice thing. You can make something easily very small. So that's why. And just to give you a flavor of what is the writing time, when we use this quite a lot, but for a smaller wafer, to illuminate all the transistors we have in RF, it's not memory, it's just RF. For a 4-inch wafer, the writing time can easily be half a day. Yeah? So that takes time. Yeah? But if you now think you buy your electronics at MediaMarkt or even Aldi, yeah, waiting for half a day for a small wafer will not work in the money. It takes simply too much time. And that is the real consequence of Moore's law. We have gotten used to buying these cheap electronics. For example, memory sticks cost €1. Yeah? And there's all these electronics in it that is only achievable if you have parallel exposure. Yeah? So that's why we need optical lithography. And then even if such a machine costs 150 million euros, if the throughput is enough wafers, it will be affordable. Yeah? So that's why you can buy stuff at Aldi, at Lidl, and you get very nice electronics with high yield for essentially nothing in comparison to the machine. Yeah? Cool. The last thing I would like to talk about, there's also some underestimated steps, for example, etching. Why do I need to etch? Yeah, because I have this strange idea. I contact these devices. Yeah, so for example, when we are putting multiple layers on top of each other, we either drill holes in them. And why should I drill a hole in a layer? That's, for example, because I want to contact the device underneath. Yeah? So, for example, to form something like this hole here to go down to the device, this is what is needed. Yeah? And what do you do? So here you see this. So etching you can really observe. So you see the wafer in there, and there's two ways of etching. There's a liquid etching, yeah, by relatively drastic liquids. So for example, we use things like hydrofluoric acid, HF, which essentially goes through everything. So you can etch semiconductors, and we need that because sometimes we just need to remove one layer, but very defined. So we use some strong etching. Yeah? And the better way to do it is to do dry etching. So you expose with a gas, something which is highly selective, especially. You put on this material and then mask it. And what do you have then? So you have the mask, the metal stuff on top, and then you want to go into the semiconductor, and you see already the trouble if you go more isotropic, so you just don't accelerate the etch, so you just leave it happen, then you get something underneath the edge, because it etches in both directions, yeah? Down and to the side. Yeah? And you can also, if you want to do a via etch, then you probably want to have a stronger bias, and you can support this etching by physical means. So you also accelerate the ions in there. That's what we call reactive ion etching. So there's a physical contribution also to the etching. So it's not only that you take the chemical exposure, so that it just etches, but that you also shoot at the crystal, yeah, with some accelerative bias of the gas. The trouble is, and remember we were talking about single atoms, so you want to expose as a trench, but you want to stop also underneath, yeah, because here could be the active transistor, and if you hit the crystal too hard, then you will also kill the conductivity of the active device. So what is very special is to have these. So here it's depicted, you want to drill a hole in this top layer, but you have the active device underneath, and if you don't do this right or too heavy, then you have a hole here, but the semiconductor underneath is gone. Yeah? And remember how a processor looks. This is not just one layer, this is 10 layers. So that's a yield question at the end of the day. Yeah? So this is also not an easy process, but it's and always what is turning us crazy these days is that you see this is obviously a macroscopic process. So you have a hole in the chamber, and then by timing you say, no, I'm waiting for 10 seconds and I'm removing one atom layer. So I wait for 20 seconds, 2 atom layers. And this is of course quite tricky, because if you miss that timing, or if there's maybe anything which doesn't belong there in the process, then there might be, the timing might not be correct, and it takes maybe 12 seconds to remove one atom, and then you're not connecting the structures underneath correctly, or you are over etching. Yeah? And all this is tricky because you want to connect 10 billion transistors. And if you don't do this right, you will lose a lot of them, and the things will not work. So that's the challenge of making it effectively happen. And then there are also some things which seem to be relatively easy. So for example, to evaporate the metal. So for example, I said you can easily put, as we did here, I said, for example, here we are putting metal, and it will grow here in a hole the same way as on the top. But this is always a bit shaky, so if you have done any cooking or whatever, you know that even if you can wet a surface with something, it doesn't mean that the liquid you put on top will necessarily go into the hole, because there's, depending especially how, if the trenches are very steep, you don't get it in correctly, or the other way around. It can be that this hole is filling while the growth here is not yet completely grown up. Yeah, so this is a very nice structure, but for example, when you then do it in reality, for example, if you remove the resist and this evaporation, what you don't want is that, for example, there's a fin going up here just on the side. Yeah, so these are all the physical problems you then have to solve. So this looks very nice in theory, that you say, I can do these blocks. In reality, you always have to prove, and this is where we are spending most of our time, that these edges are really edges and not. And you see also there's a hole drilled, and it's not perfectly rectangular, because already removing stuff out of a hole is a big problem, and that's not something which works easily. So there's always good combinations of physical procedures and chemical procedures to make it work. And this is the secret of processing that nobody talks about, that it really works. Yeah. So, and how will you realize it's good? You will realize when you then make devices and you get them in quantities. Yeah? So, for example, when we, look at the CMOS production here, we have 10 billion devices, and in 10 billion transistors, few can be dead. But if there are too many dead, then the chip will overall not function. Yeah? And you will pay this by a price. And as you know, a processor is a expensive device. So a microprocessor today costs something like 100 or 200 euros. But if you call back to the number of transistors you're getting, let's take 100 euros divided by 10 billion, which is 10 to the 10. Yeah. So per transistors, you pay, what is it? 10 to the 2 times 10 to the minus 10. So it's 10 to the minus 8. So that's nanocents, which you pay nano euros or microcents, which you pay per transistor. Yeah? And this is what you have gotten used to. Yeah? So this stuff, when you go to this regime, effectively costs nothing. Yeah? In RF, the story is a bit different. There, we really talk about single transistors. Yeah? So, for example, that is also why we should look at this graph here a bit. In your cell phone, when you have the real things which you are using, yeah, so the real RF transistors, there's maybe something like 50 transistors lined up here for the different bands. So each amplifier has one transistor at the output to make the radio waves. Yeah? So in this case, you're paying still cents per transistor. Yeah? So this is, and I told you, the CMOS is not capable of providing the power, but we would use some bipolar thing for this. Yeah? And then you're really getting a number for in terms of pricing. Yeah? So just as an idea what is different. Yeah? And maybe just to close, what are we trying to get? When we are now thinking about back to the semiconductors, what we are essentially trying to get good semiconductors. So it's not just about the processing, but it's also about the types of materials which distinguish. Yeah? And the first thing, for example, is to make some contacts around them, where you just make an assumption that it's going to happen. Yeah? But this is normally also removed. And the first thing is to explain what is the problem now about the semiconductors is we first of all have to declare ourselves what do we need. And the first thing is we can select a semiconductor. And if we take silicon, we have this band gap. And we already learned last time that the mobility, which was a guiding principle, will be better if the band gap is getting lower. Yeah. And the trick is now, which this is for this graph here, that we find, depending on what we want to do, first of all, good semiconductors, in the sense that they are transporting for the voltage enough current, so mobility is proportional to the current, while the band gap which you choose is a selection for the voltage. Yeah? And you see there's a trade-off in nature, which is mobility is good for low band gap devices and it's getting down for high band gap devices. And however, the wide band gap devices will give you a lot of voltage. Yeah? And to explain why that happens is, why do we use different semiconductors than CMOS? That's quite simple. Because when we speak about waves, there is a certain impedance we also have to match. Yeah? Because remember that vacuum gives us a certain impedance, which is, we learned that's 120 pi, 377 ohm, which gives us some kind of ratio for the impedance. Yeah? And now, where's impedance in this diagram? This is something you may want to start thinking about. This is totally physical, but where's the impedance there? It's actually quite simple. Yeah, but that's one way of looking at it. But think about if you express impedance in terms of voltage and current, what is it? How can you express impedance easily in voltage and current? What is resistance? Yeah. So it's essentially the slope of this value by this value. Yeah. And that is why you could, and the trouble is, there's a difference in RF how we can obtain power. We can do it by this, reducing the voltage very much and going to very high currents. And what we can also do is we can reduce the mobility very much and go to very high voltages. But normally you would say power is power, doesn't matter. Yeah? But that's not true, because we also, once we have done the power or created it, we need to get it to something which is defined, so in the range of 100 ohms. Yeah? So the trick is that if you start thinking about that, you will always, of course, want to be on the top side of these potential things. Yeah, but if you, exactly as you said, if I'm increasing the current further and further and further, the impedance will go down. Yeah, and that is the principal problem which you have in reality. That is that if you're doing it too much by the current, you're creating the power, but you're not getting it out. You could say, I'm not getting it out. But the trouble is, you know that with this matching we talked about, we can get always a matching. We can always, for one frequency, in doing this transformation from one impedance to the other, we can always transform one frequency from one impedance level to the next one. But unfortunately, we have this strange idea that we want to transport some bandwidth to get the information across. Yeah? And what I'm trying to convey is that what you are effectively adjusting by making the material selection is the bandwidth we get. Because, again, you can always transform from 1 ohm to 100 ohms, but your filter doing that will be... So, and that is what is already happening today with the base stations. We have to send out a certain power, so a base station which we get has 100 watts of power, and then it's not if you do it in silicon, we can do it in silicon, but it only works at a certain efficiency. And then you say, how do I make the environment better, not spending so much current in it? Then you choose other materials which have better properties, and then you are going to make the material choice. Yeah? So what I just did is to explain why that what you learn is power is not power. Power is power at some impedance, or related to it some bandwidth. Yeah? So nature gives us, apart from just having to create power, gives us two obstacles to transport over a distance, which is the losses. This you cannot change, so you cannot say, okay, I'm building my network with less power. This simply doesn't work because you wouldn't reach the people. You need simply to be near to the people, or you have to have certain power to reach you. If I'm speaking only, you will not get them information because it's absorbed. Yeah? And the other idea is that the capacity you're creating in this procedure is strongly impedance dependent. So in the selection between mobility and band gap, you're already making a choice the moment you start to select the active material. Yeah? This is not clear so apparently we have a lot of possibilities, and silicon would be an easier way to do it because we can do the manufacturing quite nicely. But the reason why we are not doing this is simply it wouldn't be efficient. And that's why in RF, depending where we are in the spectrum, we just choose the best materials, because it's still better not to waste all this power. And especially as we have such strange ideas that this thing has to work for a day and not just for 2 hours or 1 hour, then you're going from here which you can always test, you're getting to the other ones here and here and here, and also for the backbone also here. Yeah? And this is it's actually a quite simple idea, but not many people on this planet understand that efficiency is related directly to the material choice, apart from many other things, of course. But why on earth would we do this story of going away from silicon? It's an efficiency problem. Yeah? Okay. Just a preview, and we will talk about a little bit about more the trade-offs, why we need such strange devices. And the fundamental limit we'll start talking about next time is that so far we have created with the mobility, we have created the ideal motorway, but we have no carriers yet. And a motorway is only useful if you have cars on them, so carriers. Yeah? So the trick is that apart from choosing a material which has the highest mobility, we also have to make sure we get enough carriers on the motorway. And these mobilities we show here are those mobilities for essentially no carriers around. Yeah? But as traffic is the product of cars driving times a good motorway, then you get the maximum out of it. It's not useful just to talk about the motorway. If there's no cars which can drive on it, you can forget the concept. Yeah? And conduction is always number of carriers, and that's I have to go to my car now to go on a motorway. That's why I'm insisting. Carriers, number of carriers times good mobility gives you perfect traffic, and that's what we need in the device in order to get as high as possible here. Yeah? Okay. I will close a bit early for the reason I explained. I hope this is interesting. So now we have a break of 1 week, and then we will see you in 14 days, and I hope you still bear with us. We will look at some now at the mobile Nobel Prize winning devices which make this happen. So there was a couple of Nobel Prizes just to be able to build this. So we hope we can talk about this, and looking forward to doing this with you. Thank you very much.